about the analysis of statically determinate structure. So this focuses on the background of structural engineering and theories of structural analysis of determinate and indeterminate structures. So the first topic in lesson 1 is the support connection. So here, structural members are joined together in various ways depending on the intent of the designer. The three types of joints most often specified are the pin connection, the ruler support, and the fixed joint. Examples of these joints, fashioned in metal and concrete, are shown in figure 1 and 2. So here, idealized models are used in structural analysis that represent pin and fixed supports, and pin-connected and fixed-connected joints are shown in figure 3A and 3B. In this case, a more appropriate model for a support or joint might be that shown in figure 3C. For the second topic in lesson 1, the idealized structures. The head crane and trolley is shown in figure 5. For example, the framing used to support a typical floor slab in building, figure 6. On the other hand, if the framing plan is intended to represent fixed connected members, then the lines for the beams or girders would touch the column. For example, the structural graphic for the cast-in-place reinforced concrete system in figure 8 to the left is shown in top view in figure 8 to the right. The lines for the beams are dashed because they are below the slab. So the third part of our lesson 1 is tributary loadings. To illustrate the method of load transmission, consider the framing system shown in figure 10, where the beams A, B, C, D, and E, F rest on the girders A, E, and B, F. So for equation of equilibrium, the fourth part of our topic in lesson 1. So in general, the internal loading acting at the section will be consist of normal force N, shear force V, and bending moment M as shown in figure 11. So the first topic in lesson 2 is about determinacy. So here we have an example. So for the solution, R is equals 3, N is equals 1. So 3 is equals 3 times 1, that will be statically determinate. Next, R is equals 5 and N is equals 1. So 5 minus 3 times 1 is equals 2 is statically indeterminate to the second degree. Next, R is equals 6 and N is equals 2. So 6 is equals 3 times 2, that will be statically determinate. Next, R is equals 10 and N is equals 3. So 10 minus 3 times 3, that will become 1 is statically indeterminate to the first degree. Now let's go on to the second part of lesson 2, which is stability. So in improper constraint, in some cases there may be as many unknown forces as there are equation of equilibrium. So here we have an example. Now you can see the three examples that is presented here. So for the first examples that you can see, that is determinate. So the member is stable since the reactions are non-concurrent and non-parallel. For the second example, that is indeterminate. Because the compound beam is stable, it is also statically indeterminate to the second degree. So for the third and last example, the compound beam is unstable since the three reactions are parallel. So the lesson 3 is about the application of equation and equilibrium. So building frames and trusses are typical examples that are often constructed in this manner. The number of our reactions, that is equal to 9, and the number of members, we have 3. So we can say that 9 is equal to 3 times 3, so 9 is equal to 9. So therefore, we can solve those reactions using the equation of equilibrium. Here we have an example. Determine the reaction on the beam show. If we can see, we have a fixed support, and this is a cantilever beam. We have here the AX, we also have the reaction AY here, and we have the moment in A here. Now since we have 3 reactions and only 1 member, so 3 equal to 3, this is statically determinate. In order for us to solve for the reactions, let us first divide this beam into a rectangle and triangle. In here we have our reactions AX, we have here AY, we have here the moment in A. If we can observe in our triangle, we have the magnitude of 5 kN per meter, so meaning this 5 kN per meter also. And for the total, since the total of magnitude of our load in this side is 15, so this triangle is 10 kN per meter. For the resultant of load for the triangle, it will be acting at 1/3 of the distance, that is 12 divided by 3. So meaning, this is acting at 4 meters. For the magnitude, we have to compute for the area of the triangle. So there will be have 1/2, the base is 12, and the height is 10, which is equal to 60 kN. And for the rectangle, all we have to do is to compute an area. That area is just the base, which is 12 multiplied by 5, so this is also 60 kN. And this distance where our resultant is acting, that is half of the span length, which is 6 meters. So if we are going to submit forces, horizontal is equal to 0, taking the direction to the right as positive. As you can see, we have no other horizontal forces except from AX. Therefore, AX is equal to 0. And if we are going to submit forces, vertical is equal to 0, taking the upward direction as positive, then we have the AY. Since we assume that AY directed upward, so therefore it is positive minus the resultant of triangular load, which is 60 kN, minus the resultant of our rectangular load, which is also 60 kN, and is equal to 0. Therefore, AY is equal to 120 kN. Since our assumption in MA is counter, so therefore negative MA and the resultant of our triangular load is 60, that will produce clockwise rotation. So therefore, that positive 60 multiplied by the distance 4 meters. For the resultant of our load, which is 60 kN, that would create clockwise rotation also. So plus 60 multiplied by the distance of 6 meters, that is equals to 0. So solving for the value of the moment in A, that was 600 kN-meter, and since the answer we get is positive, meaning our assumption is correct, that the moment in A is counterclockwise. So for another example, we are asked to determine the reactions on the beam shown here. So we can see here at point A, we have two reactions, so horizontal reaction AX and vertical reaction AY. At point B, we have one reaction BY. So if we are going to check for the determinacy of the beam, so our R is equal to 3 and N is equal to 1. So 3 is equal to 3. This is statically determinate, meaning we can use the three equation of equilibrium, which is the assumption of forces, horizontal is equal to 0, the summation of forces vertical is equal to 0, and the summation of moment is equal to 0 in order for us to solve for the AX and AY and the BY. That's all for today. Thank you.